Alright, so we got gas stoichiometry. Sounds super tough, but if you got a good grasp on regular stoichiometry and a grasp on gas laws, then this is really just another thing. It's just these two lessons combined into one. So gas stoichiometry is the combination of your regular stoichiometry and your gas laws. So again, stoichiometry with gas laws. Kind of redundant, but that's what it is, just stoichiometry and gas laws. So if you don't remember, hopefully you do though, stoichiometry was your mole ratios between compounds and gas laws were your pressure, temperature, volume, and mole relations. So if you remember basically PervNert or PV equals nRT, and you remember how to do your stoichiometry or your balanced equation mole ratios, then this should be a walk in the park. It's just a matter of doing the conversions that are needed. One important thing to note is whether or not your chemical reaction is at STP or it's not at STP. If your chemical reaction is at STP, standard temperature and pressure, then you can consider standard volume to be 22.4 liters, and that'll come into play in a moment. If it's non-STP, then we're going to use PervNert or ideal gas law. So if it's in STP, we don't have to use ideal gas law. If it's non-STP, we have to use ideal gas law. And that'll make more sense in a moment. But the best way to learn this stuff, as always, is just to jump straight into it. So let's work out a couple problems. We'll keep it simple at first. We'll do a volume to volume problem at STP. So this is going to be volume to volume conversions at STP. You'll come to love volume to volume problems at STP because those are super simple to do. All you really have to do is multiply by your ratio, and I'll show you how that works in a moment. So let's just work out this problem. It says how many liters of water, so I'm looking for liters of water, can be made from 6 liters of oxygen. So I got 6 liters of oxygen and excess hydrogen gas. So this is excess, I'm not going to worry about it. And we're at STP, standard temperature and pressure. All right, to do stoichiometry, what is it we have to have? Well, we have to have moles. We can't compare volumes, we can't compare masses, we have to compare moles. So I got to convert 6 liters to moles. Now, if I wanted to, I could take that 6 liters, put it into ideal gas law with STP conditions, and solve for the volume if I wanted to. But since I know at STP, 1 mole of a gas takes up 22.4 liters. So I can use that instead and forego using ideal gas law. So I got 6 liters of oxygen gas. I'm going to convert that to moles of oxygen gas. So 1 mole of oxygen gas would take up 22.4 liters. So if I only got 6 liters, how many moles do I got? If 1 liter takes up 22.4. So liters of O2 cancels out. So I do 6 times 1 divided by 22.4. And I got 0.27 moles. 0.27 moles of O2. So again, I could have used ideal gas law, took this 6 liters, plugged it into PV equals nRT with a standard pressure and standard temperature and universal gas constant, and solved for volume. And it would come out to be the same thing as if I had just taken this liter amount, this volume amount, and divided it by 22.4, which is a standard volume at STP for 1 mole of a gas. Hopefully that makes a little sense to you. Alright, so now that I got some moles, I can do stoichiometry. Now normally I wouldn't have stopped in this after one step. I would have continued on in this step, so I wanted to break it down into individual parts just to get that point across. So now we'll continue on with the next step. So I got 0.27 moles of O2, and I need to change that to liters of H2O. So let's do our stoichiometry first. I want to change moles of O2 to moles of H2O. So moles of O2 go on bottom, moles of H2O go on top. Use your balanced equation for these values here. There is 1 mole of O2 for every 2 moles of H2O. So moles of O2 cancel, leaves me with moles of H2O. But I don't want to stop at moles of H2O. I want to go on to liters. I need liters. So we continue our chain. Since I got moles of H2O on top, moles of H2O go on bottom, and I want to change it to liters of H2O. So moles H2O cancel. I need some values here though. Well, 1 mole of H2O is equal to 22.4 liters since it's a gas. Remember, standard volume of an ideal gas at STP conditions is 22.4, so that's your conversion factor. Alright, now we can just do a little bit of math. So that 0.27 moles times 2 divided by 1 for my stoichiometry times 22.4 divided by 1 for my mole to volume conversion, and I get 12 liters of H2O. There's our answer. Now earlier I said a volume to volume at STP is super simple, and here's why. If you notice, we had 6 liters of oxygen and we found our answer to be 12 liters of water. So in a volume to volume at STP, all you really have to do is multiply by your ratio. Because look, from the start I divided by 22.4, and in the end I multiplied by 22.4. That cancels itself out. So all I really did was multiply by the ratio, which was 2 to 1. Those 2 waters for every 1 oxygen. So there's twice as much water. So if I got 6 liters of oxygen, that means I got 12 liters of H2O. So if you can remember that, volume to volume STP problems are super simple. Just multiply by the balanced equation ratio. Alright, let's do another one. Alright, this time we're doing how many liters of water can be made from 72 grams of oxygen gas and excess hydrogen gas at STP. So we're doing mass to volume at STP. Mass to volume to STP isn't too difficult. It's not as easy as volume to volume at STP, but it's still pretty simple. Since it's STP, anytime we're going to do a moles to volume or volume to moles conversion, we're going to use that 22.4 conversion factor. Or if you want to, you can use PV equals an RT. And for mass conversions, we're going to use our molar masses, like in regular stoichiometry. So let's break this problem down. It says how many liters of water can be made. So I'm looking for water in liters from 72 grams of oxygen gas. So I got 72 grams of this guy. Excess hydrogen, so I'm not going to pay any attention to this one. And we're at STP conditions. Alright, so let's get this thing underway. I got 72 grams, and I want to take that to liters. So I got 72 grams of O2. I'll put that over 1. Now I need to change grams of O2 to moles of O2. So grams O2 goes on bottom, moles O2 goes on top. Well, now I need some values here. Well, 1 mole of O2 is equal to 32 grams of O2. I got that number from my periodic table with oxygen being 16 grams times 2. 16 times 2 is 32. So grams O2 cancels. Once I got moles of O2, I need to change it to moles of H2O, and that's our stoichiometry. So since moles of O2 is on top, moles of O2 is on bottom, moles of H2O goes on top. Moles of O2 cancel, leaves me with moles of H2O. Now I need some values here. So I got 1 mole of O2 for every 2 moles of H2O. Once I got moles of H2O, I need to change it to liters of H2O. So let's continue this string out. So moles H2O is on top, moles H2O go on bottom, and I'm changing it to liters of H2O. So moles H2O cancel, leaving me with liters of H2O. Well, for every 1 mole of H2O, there is 22.4 liters. And there is our conversion string. So let's do some math. I got 72 times 1 divided by 32 times 2 divided by 1 times 22.4 divided by 1. And I get 100.8 liters of H2O. And there is our answer. Alright, let's do another one. So how many liters of water again? So I'm looking for liters of water. Can be made from 72 grams of oxygen gas. So we got 72 grams again. Excess hydrogen gas, we're going to ignore hydrogen, at a pressure of 10.5 atmospheres and a temperature of 75 degrees Celsius. So this time we're not at standard conditions. Since we're not at standard conditions, we use PV equals nRT to do our conversions for moles and volume. Alright, so we got a pressure of 10.5 atmospheres, a temperature of 75 degrees Celsius. We've got to change that to Kelvin, so we add 273. 75 plus 273, we get 348. Remember, always change temperature to kelvins for ideal gas law or gas laws in general. Since we're in atmospheres, I'm going to go ahead and include my R constant, which is 0.0821. Alright, now we can begin from there. We got everything picked out. So I got 72 grams of O2. Stick that over 1. I need to change grams of O2 to moles of O2. So grams of O2 go on bottom. Moles O2 go on top. 1 mole of O2 is 32 grams of O2. So grams of O2 cancel. Now we've got moles of O2. We need to change it to moles of H2O. So moles O2 go on bottom. Moles H2O go on top. Once again, it's a 1 to 2 ratio. So 1 to 2. Moles of O2 cancel. Once I got moles of H2O, I need to change it to volume of H2O. Since it's not at STP, I'm going to cut my string off right here. Once I get this moles of H2O, I'm then going to plug that into ideal gas law. So let's finish this little portion here. So I got 72 times 1 divided by 32 times 2 divided by 1. So I have 4.5 moles of H2O. Alright, that's not our answer though. We got to take moles of H2O and change it to liters of H2O. So let me slide down a little bit so I got room to work. So to change moles to volume at non-STP conditions, we use ideal gas law, we use Pervnert. So just plug in. Pressure is 10.5. Volume is what I'm looking for. Moles we found to be 4.5. Our constant is 0.0821. Temperature is 348. Now let's do a little bit of algebra. 10.5 times x is 10.5x. 4.5 times 0.0821 times 348. And we get 128.8 28.57. Divide by the value with x. That cancels. X equals 128.57 divided by 10.5. And we get 12.24. 12.24 what? Well, we're looking for volume, so that's going to be liters. There's our answer. So gas stoichiometry isn't too different from what we've been doing in the past. You just got gas laws rolled into stoichiometry. And stoichiometry is just this mole conversion right here. There's your stoichiometry. Your gas laws is just a relation of your pressure, temperature, volume, and moles. So we're just taking these two ideas and rolling it together. Now there are different version types. Like this one was a mass to volume at non-STP. So we had to use PV equals an RT. Our first problem was volume to volume at STP. So we can just use a conversion factor of 22.4. But since we divided by 22.4 and then multiplied by 22.4, it cancels itself out. So all you really have to do with volume to volume at STP is multiply by your ratio right here. That's all you really got to do. You might also see mass to volume or volume to mass at STP, in which case you got to do a mole conversion with your molar mass and a mole conversion with 22.4. Now, since this is stoichiometry, you may also see some limiting reactants. You may see some percent yield, but that is no different from regular stoichiometry versions. So don't let this stuff being in gases throw you off. The only thing we're adding to our stoichiometry is using PV equals an RT to solve for some variables. But past that, it's all the same stuff. And I hope this video helps. And as always, good luck on your tests.